Hello, my name is Mariam Qureshi. I'm a data scientist at Pivigo, and I'm going to be introducing you today to Martin Smith, who's from Ditchley. We're speaking about a project titled Exploring Networks for Influence, a graph database for the Ditchley Foundation. So a little bit about, next slide, please. Thank you. So Pivigo, our mission is to help make every business data capable. So we provide data science capabilities and support to businesses of all sizes and in all fields. What is the main barrier to a company either starting their journey with data science or moving up to the next level and becoming more sophisticated with their use of internal data is access to the right people, to the right type of talent. And that can be in terms of experience as well as diversity of skills. So Pivigo is there to solve this problem in the market. And the way in which we solve this problem, next slide please. Thank you. Is that we find people who have relevant skills in academia. The Eureka movement that created Pivigo was to think up a program called Science to Data Science, in which we invite academics with relevant technical skills, and these are people who are used to working with large data sets and with statistical rigor and applying scientific analyses and hypotheses to problems. We invite them to work on real life, usually commercial data science problems. The kind of deal is that the academics are hoping to transition into a career in data science, and they will receive commercial experience in the field. And a business is able to run a kind of a first glimpse or a proof of concept or a testing experience with science to data science. So it's a 5-week fully managed data science project. The data science project is developed in combination with Pivigo. We scope it out and we identify the right data set to use and what types of skills might be necessary in running the project. And then we find the right people. So we select a group of academics that we think are well suited, who may or may not have any commercial experience. We work with them together, we manage the project, and we deliver in 5 weeks. STDS it's both an in-person and a virtual program. Recently it's been more virtual because of events that have kept us from meeting up in person. But that means we have access to global data. So we represent over 70 nationalities, and we try and be completely inclusive of the academic community and the data science community in general. Sorry, next slide, please. So that is science to data science. We are Europe's largest data science training program. We're a training program on behalf of the academics, and we are a data science project delivery program, I suppose, to our commercial partners. Next slide, please. So who are our data scientists? Well, the answer to that question is that we are scientists. I myself have a scientific background. I did a PhD in physical chemistry and decided I would like to become a commercial data scientist, and I did STDS in 2016. And more relevantly to this presentation, we have Martin Smith, who is also, he's an astronomer, I believe. Martin, can you tell us a bit more about your scientific background?
Yes, thanks, Mariam. So indeed, I'm an astronomer. I got a PhD in astronomy, did a few postdocs, and then went on to take a faculty position in China. And so after moving around for whatever, 15 to 20 years, I wanted to move back to the UK, and I thought I should change things up a little bit and try and find a job in data science. And so one of my colleagues had done the same STDS program back in 2018. And so she recommended it to me, and yeah, so I signed up, took the challenge, and enjoyed it greatly. And then I'll tell you about the achievements that we made later on in this presentation.
Great. So some examples of work that we do. increasingly, the types of work that we're doing for commercial partners are to do with natural language processing and text analytics. But it doesn't stop there. We've delivered in predictive analytics. So, for instance, in terms of marketing and return on investment, prediction of return on investment, we work with computer vision. We've performed fraud detection. We've created recommendation engines, etc. But our topic for today is natural language processing and text analytics, and Martin's going to tell you a bit more about what we've done in that space.
Right, thanks, Miriam. So I'll start off with a bit of an introduction to the place where I work before talking about the details of the project. And so what you can see here is a photo of Ditchley Park, which is a country house based just outside of Oxford. And so what we do is we hold meetings, we bring people together to try and tackle various issues in society. And so Ditchley was founded in 1958, and so the original aim was to improve the relationship between the US and the UK. And so what our founder, Sir David Wills, was thinking was that if we had a better relationship with the US, maybe we could have prevented the Second World War. And so since then, we've branched out into many other themes, and we have quite a broad range of interests on, as I say on this slide, things like democracy, education, technology, climate, lots of different things. And so for the past 60 years, we've been bringing a number of people together to try and address these themes. And so we do this through informal discussions, because we believe that this, the important point here is to enable greater common understanding. And rather than producing reports that may or may not be read, what we want to try and do is bring together important people. And this will enable them to think new things, develop new connections, and hopefully take away a new scope for action. And so to do this, we bring together decision makers in various different sectors: government, business, academia, technology, and we try and engage as widely as possible across society. Importantly, bridging divides, because that's how we believe we can make progress. And so on the right, you can just see a bunch of meetings that we had since our inception. This is just a few years at the beginning in the 60s. So we've actually held over 730 conferences. And we can see one here that shows the importance and highlights the good work that we've been doing ever since we started. And so back in 1964, we held a conference on education by correspondence and television. And from this, the Open University was born. So we played a pivotal role in the development of the Open University, as you can see here from this newspaper article mentioning the conference that we held. So like I say, we're doing lots of different themes that we're trying to tackle. And so I'm going to tell you now about how we can use the technology that we've developed in partnership with Pivigo to try and address these aims. And so next, Miriam can tell you a bit about graph databases.
Thank you, Martin. So I suppose the question, or where data science kind of enters the story with Ditchley, is in finding efficient ways and innovative ways of storing the information about people and their relationships. And that's where graph databases really shine. They are a tool specifically created to solve this problem. Graph databases store two types of data. The first is a node, which is an entity that might be a person or an article or an organization or a company. And the other data type is a relationship. So the type of relationship that entity has with other entities. So for instance, social media, for instance, you might be friends with somebody on Facebook. Your friendship is stored as a data type as well as you and the person that you're friends with. And that has huge advantages in terms of computational power and storage. It's a very elegant way to store that type of information, as opposed to the more traditional relational database, where you might have lists of people and would have to perform a computational analysis to calculate who has relationships and what the nature of those relationships is. So The other advantage of storing this type of information in a graph database is that there are graph algorithms that can be used, which originate from graph theory. And on the next slide, the graph algorithms are hugely advantageous in calculating important metrics and describing the dynamics of networks. Sorry, just waiting for the next slide. Thank you. So graph algorithms. One example of how you could use a graph algorithm might be to perform a search of the number of people involved in a network, which is something that would be symbolized by how entities are related to one another. So the network is defined by both the entities and the relationships between them, and it's much easier to store the information about how that network is defined and who are the central entities and who might be more peripheral. So that kind of information is very easily accessible and visualized in a graph database, along with describing the nature of how, for instance, information might spread through a network. So you can see where one relationship is dependent on many entities. You can see where that information flows and who it goes through and how it's filtered, for instance. And all of these sorts of metrics and dynamics are really elegantly and quickly calculated using graph algorithms. In fact, Ditchley already had a graph algorithm in use to store this sort of information, which Martin will tell you a bit more about now.
Yeah, so before I do that, let me backtrack a little bit to historical background. So since 2004, we've been using a fairly standard SQL-based customer relationship management software called Razor's Edge. So this is very popular among non-profits and other fundraising organizations. And so, as I say, it's a traditional SQL database, but we want to try and make use of some of those advantages that Miriam just talked about in a previous slide. And so we want to use graph databases, as I say here, to harness the power of connections. And so our database is constantly evolving, and as we expand it to bring in new resources. And so I will show you in the next slide the kind of things that we have available to us in this database. So we can see here a schematic of what the database actually looks like. And now I don't expect you to read any of this, but you can see the different entities in our database and how they're related. And so the different corners. On the left, in red, we have a bunch of nodes related to the Ditchley events. So we have the event that the person attended, the name of the person that attended, the company that they work for. And then at the top part of the graph, we have information on the geography, so where these people are based, what year the event happened. And then we've supplemented this with various additional resources that can tell us something interesting when we're trying to find new people. So at the bottom, we have Companies House, which is just a list of all of the registered companies in the UK. Or we have information on the parliamentarians' activity on Twitter. We have information from the charities database. And then in the top right, we have information from the Microsoft Academic Graph, which is a large database of academic publications. And so we can use all of this information to try and help us to identify the right people for conferences. And so here's an example of how we might use the graph database. So as I say, we have information on parliamentarians, and we have information on the committees that these people have been on. So what you can see here, if I can get my cursor. So up here we have in orange 2 separate parliamentary committees. And then we have a bunch of MPs, these grey symbols, who've attended or sat on these 2 committees. And so in this side at the bottom, we have the Ditchley information. So we have a bunch of Ditchley conferences and a bunch of MPs who've attended these Ditchley conferences. But what we can do is, with very simple queries on our graph database, we can find out which MPs have attended parliamentary events and also sat on these parliamentary committees. So this will give us an idea of which of our Ditchley contacts are in a particular field. So in this example, we just looked at committees that include the word security. in them, and so we have these two on here, and then we can look at which MPs sat on these committees and also attended these events. But to do this correctly, what we need to do is we need to match our MP in our Ditchley database with an MP up here on this committee database. And so this is done with this intermediate link here, but this is really crucial that we actually know who, whether these two MPs are the same person. And so that was the focus of the first project that we undertook with Pivigo. So for the next few slides, I will talk about the work that we did on name matching. So it's very important that we know who's who. So we have this vast connected database, which is great, but we need to know that these connections are valid ones. So we can see this example on the right. We have Martin Smith, which is me, but then we also have many other Martin Smiths, which are not me, including one person in here who is actually a Ditchley governor, Sir Martin Smith. So that just shows you how easy it is to get confused when you have common names, and we need a way to kind of disambiguate these connections. So we approached Pivigo, and this was the focus of our first SQDS project back in the summer of 2019, and this is the one that I was involved in and how I started my relationship with Pivigo and with Ditchley Foundation. And so for this project, we were interested in two groups of people. One was MPs and another one was academics. And so my main focus was on the MPs section. So I'll now show you a few slides about how we tackled this problem. So we have around 600 MPs, and how many of those already exist in the Ditchley database? If you look for an exact match of one name in our database with one name in the MP database, you'll see that you get around 500 matches, which is okay, but we could do better. And so the first step is to clean the data. So if you remove titles like doctor or like QC, and if you remove hyphens and other things that get confusing, then that gives you a bit better. So then we had over 500 matches, but still it wasn't perfect. So the next step is to look at what's called fuzzy matching, where you look for matches which are not exact. So this example, we have Lee Benjamin Rowley and we have Lee B Rowley. So I mean, to me and you, this is probably the same person, but does the computer know it's the same person? Not if you're looking at exact matches, but if you look for these fuzzy matches, then you can find these kinds of matches. And in that case, you can then match every single MP to somebody in the Ditchley database. So at this point, you might think the problem is solved. But then we come back to the issue on the last slide, which is how do we know that these are actually the right matches? How do we know that these are the right names that we're getting at? And so we need to dig a little bit deeper to try and understand this. So when you run these kinds of fuzzy matching algorithms, you get a score for a match. And so each match is assigned a score from 0 to 100, where 100 means it's a very good match. And so you get things like this example here. Tom Bray is matched with a guy called Tom Burke. And so it's close, but there's still a letter that's incorrect. So even though the score is high, it's not correct. And then there are subtle errors, which are, for example, people who just have common names. So Derek Thomas, it turns out, is a common name. So we have an MP called Derek Thomas, and we also have in the Ditchley database a Sir Derek Thomas, a diplomat. So again, these are not the same people. We need to try and clean up this kind of an issue. So we can use the fact that Derek Thomas, MP, when we record his information in our database, we record the fact that he has MP as a suffix. And so that helps greatly in trying to clean up these kinds of matching. But even so, it's not foolproof because, for example, in our database, we could have issues with middle names not being recognized, or maybe nicknames. So, for example, Matt Weston is matched to Matthew Weston, and it's not a perfect match, but it is probably the same person. And so, how do we try and clean up this issue? So, the example I just gave you, where we're talking about Matt versus Matthew, that's actually fairly easy because you can just look. There's tables online of common nicknames. So instead of searching for Matt Weston in our database, we can search for Matt Weston or Matthew Weston or Matty Weston. And so that cleans it up. And so after this kind of initial exploration, we came up with the following classification system. So what we do is we clean the data and then we calculate the surname match, because if the surnames don't match, then you know that there's unlikely to be a correct match in there. So if the match score isn't perfect, then we discard it on the surname. If the surname does match perfectly, then we look at the first name. And then we use this fact that if NP is in a suffix, then that gives us a good indication that it's probably a right match. If NP is, if NP is in a suffix and the first name has a pretty good matching score, then we think, yes, we've got a match. If NP is not in the suffix, then what do we do? Then we have to be even more certain that the forename is actually the same. And so in that case, we implement a higher threshold for accepting a match. And so in that case, if the match score is very good, then we call it a match. And so once we have this kind of an algorithm, we can put all of these MPs through it, and we get a match for almost all of the MPs. And we check by hand, and the ones that weren't matching were ones that were actually not in our database. So it turns out this is a very good way of doing things. And so some examples that illustrate the importance of doing this is, even if NP is in a suffix, you still need a little bit of tolerance, because, for example, you might have data that's entered incorrectly into your database. So the top line, we have Mohammed spelt with an A or spelt with an E, and so we need to allow that. And then in the second line, you can see there's issues with encoding of characters. So sometimes things get a bit muddled up. So again, you need this kind of tolerance. But then you need a certain level to cut here, because as you can see in the third line, we have Ruth Jones, who's an MP, and she was matched to Sarah Jones in our database, who is also an MP. So the fact that we have MP as a suffix, it doesn't mean we can blindly accept all of the matches. We still have to have some level of cut to get rid of people like that. And then for people that don't have MP in their suffix, we have Joe Stevens is matched to John Stevens. And so that justifies the fact that we have this high matching score if we don't have MP in a suffix. So we did all this, and we come up with this algorithm that we think is a very good way to try and robustly match MPs. But that's quite easy to do for MPs, because there's only around 500 or 600 of them. When it comes to the academic publications, that's a much harder problem. And so my teammates on the boot camp who were dealing with this had a very different set of problems. They were dealing with huge amounts of data. So they were looking at only the computer science publications, and that alone was still 4 million publications and 12 gigabytes of data. So just the handling of the data required a lot of care and attention. And then the problem there is you have so many people, you just get so many matches. What you need to do is you need to generate a confidence score for each match. And instead of just relying on the MP suffix, which we could conveniently do for the MPs, it's much harder for an academic. So there's things that you can do, which are listed here. For example, you can look at the title. If the person has a professor or a doctor title, it's indicative that they're maybe an academic. You can look at their institution, so the institution that they publish under versus the institution that is listed in our database. You could also look at the field of study and compare that to the title of the event which they attended. And then the other thing you can look at is the year of publication. So, for example, if somebody attended a Ditchley event in 2007 and they're publishing in the same field in 2012, you're probably fairly confident that it could be the same person. Whereas if they attended an event in the 60s and then there's somebody publishing in this decade on machine learning, then maybe it's not the same person. So it was a much harder process trying to do it for the academics, but that was the work that was undertaken. And so in the next slide, I'm going to tell you a bit about the impact of the work that we were doing. So as well as the preliminary exploration of matching, we did some preliminary exploration of the tweets that the MPs were doing, because we also had that information. And so we can see at the bottom here, we have an illustration showing the distribution of topics that were being tweeted about in our sample of data. So, you know, there's like 10% of tweets are typically on issues related to police or crime. There's various things on like health or funding of political parties, this kind of thing. So, you know, this is an average distribution. So the larger this bar is, the more prevalent they are at talking about this. So that's averaged over all of the MPs. But what you can do is, if you look at each MP individually, you can look at how they compare to this overall distribution. So if you remember last summer, there was an issue called Brexit, which we were talking a lot about. And so here we could find one MP who was very excited by Brexit. And it turns out that almost half of his tweets, when we did the modeling of the different topics, was indeed on this Brexit-related theme here. And so we can do this kind of analysis on the tweets. And so we did this exploration, and just to try and explore what you can do and what's possible with this kind of a data set. So it wasn't part of the original challenge, but our team was able to try and push further and try and do this kind of work. And then we were also very excited to try and understand the uses for what we were doing. And so, for example, the academic database, we thought about what kinds of use cases you could do once you had this connected database. So one thing that we thought about is you can use this to try and identify which new collaborations were forged from attending a Ditchley event. So you could look at which two academics were not publishing papers before a Ditchley event, and then which academics were publishing together after a Ditchley event. So we could try and get some idea of whether, by coming to Ditchley, we've helped to forge these kinds of new collaborations. And so we didn't implement this because technically it's quite challenging, but we were able to try and think about how you could use this. And so that's something that at Ditchley now we're currently thinking about, is to try and utilize this as the use case I showed you earlier, these kinds of ideas for how to do this matching and exploration effectively. Okay, so I will now talk about the second project that we did. So after taking part in the bootcamp last summer, I was retained by the Ditchley Foundation, and so I then helped them with the mentoring of a second project, which was done on the virtual program in, I think, October last year. And so this was related to the analysis of articles in the media, so newspaper articles. So as I said before, what we really need to do is we need to identify the best people to engage with. I mean, our meetings are not going to be useful unless we have the right people in the room. And so newspapers provide a huge amount of information on people and on organizations, but then how do we get to this information? So that was this second project. And so we tasked the team with developing versatile tools to classify articles, to identify the people and organizations that were listed, and then build a queryable graph database using this information.
Just wanted to see.
And Miriam, maybe you can mute yourself. So this is an example of how the extracting the information works. And so what we did is we focused on The Guardian because there's no paywall to worry about, so it's freely accessible data. And then we applied a technique called name density recognition to try and identify the people. So you can see here, this is an article from The Guardian, and highlighted in the different colors, we have the different things that were pulled out by this technique. And so in purple, you can see it pulls out people like Samuel Toombs here. But it's not perfect. Sometimes it pulls out things like here we have Pantheon Macroeconomics labeled as a person. It's not a person. But then it also pulls out organizations, like here you have Halifax and Nationwide pulled out correctly. So once you have all of these articles from the last 10 years, you can then put them through this name density recognition to try and identify all the different people and organizations. And then you can try and put it together into this graph database. And so what the S2DS team did was they built an automated pipeline to build the database. And so it allows us to carry out efficient queries to identify what could be very complex relationships. And so Miriam explained to you how a graph database works. And so you have all of these different pieces of information stored in nodes, and then you have relationships between these nodes. So you have an article which could be classified under a topic, or an article which mentions a person. And I can now show you an example of how that works graphically. So you can see here we have an organization called EdXL, this big green circle here. And so this was mentioned in 3 articles, these small gray circles. And so these articles were authored by these orange nodes here. And so you can already see that which authors, which people, which journalists are writing articles about particular companies you might be interested in. And so this is just a very simple example, but you can then look at much more complicated examples, such as this one here. And so this one shows the Department for Education. So the green dots at the center here, Department for Education, and the gray dots are now small and you can't see them. They're basically these things here that connect these purple and blue lines here. So lots and lots of articles talking about the Department for Education. And so this is important because you can find out who the relevant authors are who are, let's say, publishing articles related to the Department for Education. And so I should say that during the S2DS project, because it's a compressed timescale, we only have 5 weeks to work on it. We focused solely on education for this test case, and that's why we're pulling out these examples here. But you can also do other things. For example, you can look at which people appear in articles together with the Department for Education. So that then could tell you which kinds of people that we should be looking for if that's what we're interested in. And so you can see here, what you can do is you can just take some keywords. For example, we were interested in further education and vocational education, and you can just look at which people appear most in articles with these keywords. And so you get obvious people like Michael Gove, who I guess was Education Secretary. But as you go further down, you can get more interesting names that you might not have previously thought of. And so a table like this is very, very easy to produce using a graph database. So we use Neo4j, and so with just one simple 1-line or 2-line query, we can pull out these kinds of complicated queries. And then here's another example. You can look at the relevant organizations. And so again, the top organizations are maybe not surprised, the Department for Education, but then the further down you get in this list, again, you're getting more interesting examples. Okay, Miriam, so you can now tell us a little bit about the business value that we obtained from this project.
Yeah, that's very interesting. I have a quick question about the above. Were you able to extract chronological information as well about the authorship of those articles?
Yeah. So sorry, I passed over it quickly, but in that table, we pulled out the name of the person, but then we also pulled out the years that they appeared in articles. So then you can tell if you've got 10 years of articles, maybe you don't want to care too much about the early 2010s, but then you can look on the more recent ones. So again, it's very easy to pull that out with a simple Cypher query.
That's really interesting. So you could see the kind of up-and-coming figures on a given topic and maybe more established figures and make a differentiate between them using this as well?
Yeah, you could definitely do that, yeah.
Yeah, very interesting. So, I mean, to sum up, right, how has this tool been used by Ditchley and what were they able to do? So this particular example, this 5-week project, from it, 30,000 articles on education, 80,000 people and organizations were extracted, 270,000 connections were described, and it yielded a graph with around 115,000 nodes and 550,000 relationships. So an immense amount of information that's captured over, I think you mentioned more than a decade, particularly on education. of that kind of information being captured and displayed and being able to be analyzed. Huge efficiencies were made over manual labeling, for instance, which would have been, I guess, the original way of doing this. And in fact, probably efficiencies over using a relational database as well, computational efficiencies, that is. I think another deliverable by S2DS towards the Ditchley Foundation in this case was a pipeline. So this can be expanded not only to cover education, but other topics as well. You know, discuss Brexit briefly, climate change, etc. It can be expanded because there's nothing specific to education that's in the underlying technology. In addition to that, this was only one news source. So for instance, this was articles from the Guardian newspaper, but given a larger data set of other news sources, this could be either supplemented or adapted to alternative news sources as well. And I believe that has created efficiencies and expanded the reach of the Ditchley Foundation.
Yeah, I think that's definitely true. We have just run the whole pipeline on all Guardian articles from the last 3 years, so we now have a much larger database that we can query. But in the next few slides, I'm going to tell you a bit about some work that we did on this education front, which also shows you the next steps that we're going to take in our relationship with Pivigo and S2DS. So Twitter is a fantastic resource for understanding social networks. And so you can use them to try and understand who people are following and also where they get their information from. And so you can look at the shape of networks to understand who is central in this network, who may be connecting. And so, like I said, Twitter is very useful. And so we have an example on the right where you can see 5 different Twitter accounts and who follows who. And so these come from a larger database that we created on the subject of education. So following on from the Guardian analysis work, we used that together with a bunch of human researchers to come up with a large database of 300 or 400 people working in the field of education and also democracy. So we're looking at the intersection of these two fields. And so we took these few hundred people and we looked at their Twitter accounts, and we didn't really do a lot of analysis with it, but we saw that it's a very powerful resource. If I can get my next slide up. So this is the active Twitter users from this sample. And so it's color coded by the purple colors relate to education and the yellow colors and orange colors relate to democracy. And you can see that there's a kind of a segregation in this network. You can see that on the right side, you have mostly education people, on the left you have mostly democracy people, but you can already see that there's a bit of mixing between these two groups. So that will give you an idea of which kinds of people would be good to try and bridge these subjects. And then you also see some people that are kind of on the outside of this network that aren't connected to many people, so those might be important people to bring into a conversation. So you can see that Twitter is a very powerful resource. And so here's a couple of examples of the kinds of things that you can calculate, similar to what Miriam showed at the beginning when she was introducing graph databases. So you can look at who are the important people. So you could just look at how many followers a person has, but that doesn't really tell you all of the information. So if you look here, you can see a graph. We have somebody called Doug here in the center who has lots of followers. And so he's represented by a large circle. But then you get somebody like Mark here who only has 1 follower, but his follower is Doug who has lots of followers. So we might therefore think that Mark is in some way more important in this network. Unlike somebody over here, like David, who has 1 follower, but his follower is in some sense not as important as Mark's follower. So you can try and do these kinds of high-level statistics to try and extract information on your data. And there's another example. You can look at who are connectors in this network. So you have people, for example, again here. So the size of the symbol relates to how much they connect different people. So you have people like Bridget or Charles that don't connect a lot of people in this graph, and so the symbols are very small. But then you have somebody like Jason who bridges these two different disconnected portions. And so it would be very important to have people like Jason in a discussion who can bring these different groups together. And so that's going to be the focus of our next partnership with S2DS, trying to utilize Twitter to extract fully all of this rich information that's contained within. And so that's the focus of our next partnership. So I urge you all to stay tuned, and hopefully I can tell you about that later. But before I finish, I should mention a few credits. And so first and foremost to the S2DS boot campers themselves, who did all of the work and produced some of the plots that I've shown in my slides so far. And I should also thank the Ditchley team and also the Pivigo team, both of whom were vital to producing this work. And I'll stop there. So thank you.
Once again, thank you to everyone for listening and for speaking, and I hope you have a great afternoon.